I guess people have gone off to spring break early. Yeah, it's even more sparse than before. All right, so let's discuss one particular graph search strategy called depth-first search, which many of you are familiar with, and see some properties that are useful in algorithm design. Why is depth-first search useful, right? So, I mean, it is a variant of the basic search. If you just want to do reachability, you don't need depth-first search. It's one strategy, but it has some very interesting properties. In fact, John Hopcroft and Bob Tarjan, the Turing Award winners, they won the Turing Award mainly in developing fast algorithms for basic graph problems, and they used depth-first search to show that you can solve problems that seem a little difficult in linear time, and so you know it's actually a very nice algorithm. You will see one of these problems in your homework, and we'll see today the strong connected components. And if you are interested in planar graphs, there's a linear time algorithm to check whether a graph is planar, and many more applications. Okay. Depth-first search is best understood probably recursively rather than iteratively, so forget about this. So depth-first search, if you want to do it from a specific vertex, right? You search a graph and you start from a specific vertex U, right? How does it work? So you initially mark all the vertices as unvisited, right? You haven't touched anything. Since you're starting the depth-first search at U, you mark U as visited. And then you look at all the edges out of U, right? This is an undirected graph for now. We're looking at undirected graphs. So you look at all the edges going out of U, and if you find one by one, right? Not all at the same time, you look at each edge, look at the other endpoint. If V is not already visited, that means you have discovered a new vertex, right? Okay. So you immediately try to explore the graph from that vertex rather than wait, right? So depth-first search is that you're going deep, right? So if you find a new vertex, you add that edge to your tree because you've discovered a new vertex, and you explore that vertex right away, recursively, right? All right. That's what this simple exploration strategy is. Right? It's one variation of a basic search, right? As soon as you discover a new vertex, you start exploring from that recursively, right? What happens when you come back from that call? When you come back from that call, you keep exploring this vertex, all the edges out of U, because you have not done yet, right? So you look at the next edge. Maybe you already found the other endpoint and it's visited, and you don't worry about it. But if you find a new vertex, then you go down that path, right? So when you have a tree, what happens, right? If I give you a tree and I start exploring the tree at a root, what depth-first search does is goes down all the way to a leaf, right, along a path, and then it comes back up one level, then goes back again down, right? So it explores the tree in a depth-first fashion, right? So on a tree, it's very easy to see what it does, right? The question is, does it have some interesting properties that enable it to discover something like a tree structure in a general graph? That's why it's interesting, right? Not on a tree. On a tree, everything is kind of easy, right? So what does it do in a graph? Okay, that's from a single vertex. If you want to explore, what do you do in general in an undirected graph? Once you find all the connected component containing that vertex U, you look at any other vertex which is not explored already, and you explore from that vertex. So it's mainly interesting from exploring from a single vertex. Okay. So there is so now when you do it on a graph, we would like to know, does this depth-first search have some interesting property, right? Okay, so how do we figure that out? Let's do that by exploring, you can just look at one connected component. Pick a vertex that you want to explore the graph from. I want to introduce some randomness in this process. 5, okay. So you start exploring from 5, and so we look at the edges out of 5, maybe in some order, right? Which which edge do you want to explore first? 3? Who said? Yeah. Any vertex? maybe we look at the 3 edges, right? I mean 4 edges, but in some order given by the adjacency list, perhaps. So we look at maybe 3 for simplicity, right? And we discovered 3 because it's not visited, right? So we mark 3 as visited, but now recursively we explore from 3 now, right? Okay. So what will 3 do? 3 will look at its edges. Maybe it finds 8 and says, okay, 8 is not visited, right? Yeah. Okay. And now we go to the call for 8, right? And what does 8 do? It has 2 edges incident to it, right? 3 and to 7. So if it finds 3 first, it's already visited, so it doesn't do anything, right? Okay, but if it will find 7 for sure, right? So it will add 7. And what does 7 do? 7 looks at its 2 edges, right? 3 and 8, and both are already visited, so it returns its call because there's nothing to discover. So we go back one level up because we are in the recursion. We go back up to 8, and what does 8 do at this point? Well, 8 already explored all its children, right? Because 3 is already visited, so it goes back up, right? Nothing to do. So we go back up to 3, right? So now we're back at 3. 3 looks at what has it explored? It has explored this edge already. It looks at 3, 7. 7 is already visited. 5 is already visited. So it will look at one of these 2 edges. Maybe, we don't know which one, but that depends on the adjacency order. So maybe it picks what? 1, say, okay? And now we go to 1. And 1 looks at its 2 edges. Well, this is already visited. It finds 2, right? Which is unvisited, and it goes to 2. And what does 2 do? 2 looks at all its edges, right? What is the only vertex that it can, it only can find 4 that it has not visited, right? And it looks at 4, and 4 has already, once it gets to 4, 4 cannot find anything else because 5 is visited and 2 is visited, and so 4 returns the call, and we go back all the way up to 3, and we're kind of done, right? 3 goes back up to 1, and that's okay. Now, while it is visiting this, right? So we call these the tree edges, right? What is a tree edge? A tree edge is the edge through which it was discovered. A node is discovered, right? Okay, yeah. Oh, 6. Oh, sorry. Good. Okay, 5 has to discover 6, I guess. That's when it comes, and 6. Yeah. Okay, good. Okay. So now let's do one thing which is interesting, right? Let's look at all the edges which are not in this tree. Okay, edges in the graph which are not in this tree. Okay, let's draw them, right? So when is an edge not in a tree, by the way? So why is an edge not in a tree? Because when we explore that edge from a node, we have already visited that node, right? So let's draw all those edges, right? So when we explore from 5, let's see where are all the edges. 2 to 3 is an edge, right? Yeah. And 4 to 5 is an edge, right? Yeah. And what else? 7 to 3 is an edge. Anything else? 5 to 2. No, 5 to 2 is 5 to 2, yes. Okay. Yes, anything else? 5 to 3, yeah, okay. What property do you notice about these red edges? Is there anything nice property you recognize about these red edges? Yeah, the important property is that a red edge is there only between a node and one of its descendants. I don't have an edge from 8 to 6, right? Well, in this case, I don't, right? But that's true of any DFS tree. in any DFS tree, I can't have a non-tree edge connecting a node and somebody which is not an ancestor or a descendant of it. Okay, why is that? Okay, so the DFS exploration creates a tree of discovery, right? I can't have a non-tree edge which is a red edge which is connecting, say, a node and something which is not an ancestor or descendant of it. Why should that not be possible? Okay, can you see why that's not possible? Because of the way we are exploring the graph, yeah? Yeah, so if in fact there is an edge connecting two, non-tree edge connecting two nodes which are not related in an ancestor-descendant relationship, look at the first guy who was visited, right, among those two, right? He should discover the other guy under itself, right? He has to be the other guy has to be a descendant of itself, right? Because we are recursing on that, right? So everything that I can reach should be below me. It can't be somewhere else in another part of the tree, okay? That's the reason why you cannot have these cross edges, okay? That's a very important part of why DFS explores the graph in a very interesting way, okay? This is the only crucial property you need to remember, okay? That it doesn't matter in the way I broke ties, right? Once I find a DFS tree, all the non-tree edges have this property that they go only up to their ancestor. Okay, that's a very important property in the way DFS explores. This is not going to be true for a BFS tree, right? Okay, you can imagine that it is not true for a BFS tree because as soon as I can have a lot of cross edges actually, right? So, but BFS explores in a different way. So this is the property of DFS. Okay, all right. So one important useful information that you can keep track of, in addition to this tree, is a notion of time. Okay, so when did I discover, and when did I come back to the same node? Okay, so let's add times to this, right? So we keep track of time as we are visiting nodes, right? So initially, whenever we visit a node for the first time, we say that we associate a time with it which is the pre-visit time, okay? So we associate two numbers, the pre-visit time and a post-visit time, okay? So when did we first enter this recursive call for this node, okay? First time. See, whenever we visit for the first time, we are going to start a recursion there, right? So we associate a time with that. And when we come back to that node and we get out of that node, because we finished the recursive call, we associate a time with that. Okay? So it is how long, what is the time interval during which this node was active on the recursion stack. Okay? So we associate a pre-visit and a post-visit. See, if you look at the code, when we enter the call, we put pre-visit and increment the time. And when we finish the call for that node, we put a post-visit time. Okay? So let's do that in the same example. So when we enter, we put, I'll use a different color so that it's like starting a stack, right? So this I start with time 1, right? Because that's the first, I initialize the time to 1, and the pre-visit time of 5 is 1, right? And then I go to 3. Time becomes 2, so its pre-visit time becomes 2, and then I go down to 8, its time becomes 3, I go down to 7, its time becomes 4, and now 7 doesn't discover anything and finishes its call, right? So when it finishes its call, I increment the time and it says its post-visit time is 5, okay? And then I go back up in the recursion at 8, I have nothing more to do, so my time will be 6, right? My post-visit time will be 6. Then I go back to 3, but then I keep going down, right? So what is its pre-visit time? 7, right? And this guy is 8, this guy is 9, and then I finish this guy at 10. Oops. And this guy is 11, this guy is 12, and then I come back and then I put 13 here because I'm done with this. I go back up, I come back, 14, 15, and 16. Okay? That makes sense, what we did? Okay? So what does these numbers mean? That this node 3 is on the stack from time 2 to 13, right? We didn't finish its call till time 13 because we are exploring below, right? Okay? So these are called pre-visit and post-visit times. These numbers have useful information, how long I've been on the stack, right? Okay? I mean, you can do it for a tree too, right? If you do it for a tree, then the post-visit numbers gives you a post-order traversal of the tree, right? Okay. So what properties do these numbers have? The numbers have this intuitive properties that the node U is active in the time interval pre-U and post-U, right? And what is a crucial property about the way we are exploring this, because it's of the recursion, for any two nodes, how do these intervals look like? Okay, each of them is a time interval, no? So my claim is that for any two nodes, either the time intervals are completely disjoint or one is contained in the other. Okay, right? I can't have overlapping, right, because of the way I'm doing recursion. Yeah, so that's an important property, right? You know, and you can. I'll not do the formal proof, but you can take a look. Okay, so that's all I'm going to tell you about undirected graph DFS. Okay, because it has some nice properties, but the crucial properties you need to know is that there are no cross edges, only back edges to the ancestor, right? That's the useful property. Yeah. No, we increment time. So for the leaf node, we actually increment time. So it is 4 and 5. Okay, so we increment time. Otherwise, it will get confusing. So okay, yeah. So if you look at the code, whenever we add a certain number, we increment it. Okay, okay. So that's undirected graphs. And directed graphs will look different. Okay, the directed graphs are always going to look a little different. I mean, not always, but you can do the same thing in directed graph. Okay, okay. Now, in an undirected graph, if you start exploring from a vertex U, what will you find? You'll find all the connected components, right? Okay. So then what happens is that you find a tree there, and then you find the next guy. I mean, if there is anybody left unexplored, you will find the next guy, and you'll explore that connected component. So you'll get a collection, right? A forest you'll get, right? Okay, in directed graphs, things are a little tricky. No, I can start exploring from a particular node, right? What will I find if I start exploring from a particular node? All the nodes I can reach, right? Okay. But maybe it's not the entire graph, right? But then what should I do next? Okay, you may say, oh, look, you know, I should start exploring from a node which has not been visited before, right? But that node, when you're exploring, may hit something that I already explored in the first DFS. So then it doesn't seem that useful actually to do that. Okay, okay, so we'll see an example. But it turns out that it still is very useful, right? It is counterintuitive. It is not immediately obvious that it has any value. But let me show you, the algorithm is the same, okay? What do? You initialize all nodes as unvisited, right? You start time to be 0, and you do the same recursive exploration, but now it's a directed graph, so you're only looking at the outgoing edges, okay? But the important thing is that this is DFS of the entire graph, and this is DFS of a specific node, right? But you keep on doing DFS as long as there are unvisited nodes. And this doesn't seem at first to have any useful value, but we will see that it has value. Okay, okay. So let me do 2 DFSs for you in this graph, right? And you'll see the why that there is a difference. Okay, and Okay, suppose I start exploring the graph from A. Okay, let's explore from A. What happens if I explore from A? I'll put numbers here. Okay, what will happen if I explore from A? I mean I have choices, so I'll make some choices, right? Maybe I'll do B, right? And B will explore. Maybe the only thing it'll discover is E. And what will E do? E will discover maybe G, right? 4, and then G cannot find anything else, so we come back. Then what will E explore? Sorry, or F or H, right? Maybe I will put F for simplicity. It doesn't matter. 6, 7, right? And then you come back up, and then E discovers H, and you come back up to E. It's done. Come back up to B. It's done. Go back up to A, and then D, right? What are the numbers? 12, 13, 14, 15, 16. Okay? Yeah? Seems okay? Okay. Now let's do the same thing, but we start from, say, some other node which is not in this. Suppose I start from, what would you like to start from? Okay. Say we start from simplicity, let's say E, just to illustrate a point. Okay? Okay? Sorry? I didn't do what? F? Oh, where did I miss F? Where should F be? F should come from E, right? Oh, this is F. This is F. My handwriting is bad. Okay, sorry. Yeah. Okay. Okay. F. Okay. Okay. So let me see. Okay. Okay. Does this make sense? Can I erase this because I don't have space, or maybe I'll. Okay. Let me try to do it in this space, right? Let's start exploring from E, say. Okay, I want to illustrate a point. So what happens when you explore from E? You'll get maybe F, and then you'll get B, right? Okay, and then you go back up, right? F will find G, and you come back up, and then E will find H, right? And that's it, right? It can't reach anybody else. Okay. Okay, let me put some numbers here because it will be important. 2, right? 3, 4, 5, 6, and 2, 7, 8, 9, and 1, 10, right? Okay, it seems, okay, now what is left to explore? A, C, D, right? You pick anything, right? Okay. So what does the algorithm say? Start with, say, A for simplicity, right? So what number should we give to A now? Okay, we say 11. What will A discover? Okay, it discovers C, right? And C discovers D, and you can put numbers here, I won't, okay? But see, there are lots of edges which we didn't add to this, right? This is the tree edges, right? So let's put those edges, I mean, in, right? You know, those that we didn't, which we discovered when we were, so I mean, we can put these edges, no? This is an edge that is not in the tree, right? Why was that edge not in the tree? Because B was already visited, no? Okay. This seems odd, right? I'm trying to make the point that, yeah. No, that's a non-tree edge. Okay, that's why I'm putting in red, right? It's not an edge, right? In the tree that we're exploring, because we add an edge only if it's visited, right? So I'm trying to add what are all the edges not in the tree but are in the graph. Okay. Sorry. Oh, no, not A, B. Okay, sorry. That is E. Sorry. Okay, that's what you're trying to say. Okay. Not to E, right? So A to B, right? The B, you know, D to A is an edge, and H to G is an edge, right? H to G is an edge, and so on and so forth. E to F, no, okay. F to B, okay, that's there. E to F, E to G, E to H. E to H is there, yeah, okay. Anything else? Sorry, A to B, right? No, A to B is there. A to F. A to F is also an edge. Okay. Okay? Okay, so you notice that unlike the undirected graph case, you have a kind of a cross edge, right? Yeah? I mean, there's an edge from H to G, right, which are not related. Okay? Okay? Okay, so what is the meaning of this? They form, I mean, if you look at the blue edges, they form what are called directed out trees, right? They look like an out tree, right? And obviously the output of this DFS of G depends on in which order you explode, right? Yeah, because if I chose to explore from A, I discovered everything. If I chose to explore from E, I get something bizarre, right? Looks bizarre, right? Obviously the first call to E will find everything that E can reach. But after that it seems like, what is this doing? Does it have any value, right? Okay? Okay, so we'll see it has some value, right? If you're only interested in reachability, you should just do basic search or just explore from a single vertex. But I claim that this procedure also has some value, okay? Okay, so we'll have some basic properties. Again, even though we do this exploration, you still have this property that these intervals are either disjoint or one is contained in another. Okay, that property still holds true in directed graphs. Okay, for every two nodes, the intervals are either disjoint or one is contained in the other. Again, this is because of the recursive nature of the algorithm. All right, that doesn't change. Okay, so as I said, it's not obvious whether this has any value or not. Okay, let's see why it is value. So, unlike the undirected graph, we'll classify these edges into 4 types. The whole graph edges into 4 types. There are 3 edges, which are the blue edges that we discovered. A forward edge is an edge which goes from a node to its descendant. Okay. So, what is the forward edge in this graph? The red arrow, is it a forward edge? Yeah, so no, okay, so which is a non-tree edge, okay, so you have to be careful. It's a non-tree edge which is going to a descendant, okay. In this case, there is a no forward edge, right? Why is there no forward edge here? Because tree edge is the blue edges. All the blue edges are the tree edges. A non-tree edge which goes from a node to its descendant. These are not their descendants, right? Because this tree is different from this tree, there's no connection. I just drew the red edges. Right? Yeah. The red edges are the non-tree edges, right? Okay. So that's not, there are no forward edges. Okay, so it's a bit messy. I'm sorry, but that's how it is. Okay. What is a backward edge? A backward edge is a non-tree edge such that you go back from that node to one of its parent. Okay. Okay. In this case, is there a non-tree edge? So F to B, and sorry, E to A, D to A is a non-tree. That's a backward edge, right? D to A is a backward edge. Yeah, does it make sense? That is a backward edge. It's going from a node to its ancestor. So this is A is an ancestor of D in this tree, right? And so that's the backward edge. Yeah. Okay. Yeah. No. We have a graph. We did DFS on the graph. The DFS creates a collection of trees. Okay. And there are edges. These are the tree edges are the edges that we add when we discover a node for the first time. No, but look, we started from exploration from here, and then we still couldn't discover these things, so we started another exploration. Yeah, the root of this tree. Then there is a root of another tree, right? Yeah, so that's okay. So you get all these complicated edges which you don't get in undirected graph. So in fact, you can get a lot of different edges. Okay, so the question I would like to ask is, does DFS give us some information or not, right? So I claim it gives us some information. Here is a question to understand that. If I give an undirected graph, how do we check whether it has a cycle and output 1 if it has 1? Sorry? First one. I give an undirected graph, how do you check if it has a cycle? I asked this too, but I'm saying, now I'm asking it again, right? Can DFS help discover it? Yeah. Right. Yeah. Right. How does DFS discover? If I do a DFS on a graph, can I find out whether it has a cycle or not? Yeah. It's an edge which is not a non-tree edge, right? If you have a non-tree edge in an undirected graph, you have a cycle. Otherwise, there is no cycle. Yeah. Agreed? Makes sense? In an undirected graph. What about a directed graph? Okay. It's a little bit trickier for a directed graph. Okay. If I have a backward edge, I definitely have a cycle, no? Yeah? Is that clear that if I have a backward edge, I have a cycle? Because it's a descendant of me and I'm going back, so it creates a cycle. Yeah, this is a directed graph. Undirected graph, if I have a non-tree edge, then I have a cycle, right? Okay, because I don't want to just have to be a little bit careful in undirected graph to talk about it as a backward as a forward edge, right? There's no orientation, so we just talk about a non-tree edge. It is not clear that there's an orientation, it's going back or it's, right? You have to be a little careful. No, this is in a directed graph. I'm going back to undirected graph, there is no notion of direction. So in an undirected graph, all you have are, it's better to think of them as non-tree edges. Should you think of it as backward edge or forward edge? How do you want to think about it? I want to just think of this as a non-tree edge. Okay, all right? Okay, that's why you have to be careful. Okay, my claim is, even in directed graphs, the following is true. Given a directed graph, how do we check whether it's a cycle? Remember, we already found an algorithm to check whether there is a cycle by doing that topological sort ordering, right? If there is a source, take it out, you keep on doing it, and if you ever get stuck, there is a cycle, right? That's one way of doing it. But I claim DFS will give us another way of doing it, and it has some applications, right? Okay, one thing is clear. If I find a backward edge, I know there is a cycle, right? What is less clear is that if the graph has a cycle, then DFS will always discover a backward edge. Okay. I claim it is not obvious. Okay. Yeah. A cross edge is an edge which goes from a node to somebody who is neither a descendant or an ancestor. Okay. So here is the algorithm, here is a nice property of DFS in directed graphs. Okay, you do a DFS of G, not about U, right? DFS of G, like we did. Here is the algorithm. You compute the DFS, right? What does the DFS give you along with the tree? It gives you this numbering, right? Post and pre and post. Okay. If during DFS you ever discover a backward edge, you know that there is a cycle in the graph, right? And it means that the graph is not a DAG. Yeah. Okay. My claim is the converse is also true, that if there is a cycle in the graph, DFS will discover a backward edge. Okay. Irrespective of the order in which you do the DFS, right? I mean, remember DFS, you start with some node, you finish it, and then if there's anybody unvisited, you do that algorithm, which looks a little strange because it doesn't seem to have nice properties, but it has some nice properties. Okay. Okay. Is it clear what I said? Yeah. That's a property I need to prove to you because it's not obvious. Okay. Second property is that if you don't discover a backward edge, if you believe me, then the graph is acyclic. Okay. Then you like to find a topological sort of it, right? Okay. I claim if you don't find ever a backward edge, then the post-visit order of the nodes will give you the topological sort. Okay. Sorting the nodes in decreasing post-visit order will give you a topological sort. Okay. Is a claim clear? Okay. First, you may say, I have to sort. You don't have to sort because DFS gives you the vertices in decreasing post-visit order. Okay. You don't have to sort it. It will give it to you in that order if you want. Okay. So in linear time, you can generate the vertices in the post-visit order. Okay. So okay. So I want you to think about this algorithm, right? You're not quite sure if this is correct or not, but I'm claiming that this is a correct algorithm. You do DFS of the directed graph, and if you ever discover a backward edge, you know there is a cycle. Okay, and I claim that you will discover a backward edge if there is a cycle. Yeah.
Same thing you said.
No, it's not the same thing because no, it's not the same thing. No, I can see cross edges also. No, I can see node multiple times, but I may not see a backward edge. Yeah, okay. I'll give you an example of a DAG where you will see a node many times, but you won't. There is no cycle. Okay. Yeah, this is a little bit more subtle because in directed graphs there could be many different types. Is the algorithm clear? What I'm claiming, right? Yeah. Okay. So this algorithm runs in linear time, right? So this is another algorithm to check whether a graph is a DAG, and it will give you a nice information. Okay. Okay. So why is it the case that if there is a cycle, it will actually discover a backward edge? I have to prove it to you, right? Okay. My claim is the following. Suppose there is a cycle in the graph, right? All right. First, if there's a backward edge, there's a cycle. Okay, let the cycle be V1, V2, Vk to V1, right? There is a cycle in the graph, yeah? Okay. So you must visit, the DFS will visit every node, right? Yeah, DFS visit every node by construction. So look at the first node that it will visit in this cycle, okay? I don't know what that is because it depends on how I break ties, right? So at some point in this cycle, I'm going to visit a node in the cycle for the first time, right? Let's call that Vi. Okay. When I touch Vi, what am I guaranteed? Sorry, I know that all the nodes in the cycle are reachable from Vi, right? So I will discover all of them basically under Vi, right? Okay, but then what happens to the edge Vi minus 1 Vi? Vi minus 1 will be a descendant of me, and so Vi minus 1 Vi will be a backward edge. Okay. So DFS will discover a backward edge if there is a cycle in the graph. Okay. All right. You see, a very important property is that not all cycles will be discovered by DFS. Not all cycles will be discovered by DFS. Okay. That, and we can't tell that, right? Okay. So this is just saying that at least one backward edge will be discovered. Okay. Okay. One cycle, right? You know, so other cycles might not be discovered. So you have to be a little careful on that. Okay. Okay. So so let's run this on this DAG, right? You know, if you run DFS on this, what will I find out, right? It depends on which order you discover. You know, if you run DFS on this DAG, depending on where you start, you may generate many different DFS explorations of this DAG, right? And for all of them, you can show that the post-visit numbering gives you a topological sort. If you don't, you see, when you run it on a DAG, you won't discover any backward edges, right? Because there are no cycles. And then my claim is that if you sort the nodes in the post-visit order, you will get a topological sort, okay, of the DAG. So if G is a DAG and the post-visit number of V is bigger than the post-visit number of U, then UV is not in G. Okay, this is a property I'm not going to prove, but let me run in an example and you will see what I'm claiming, right? So start exploring this as a DAG from some node. Let's start with B, say. Okay. If you start with B, what is the number I give it? 1. And then I have to go to E, and I have choice here. I can go, I get 4. Then this guy goes to 5, 6. And I'm done, right? Sorry. 7, 8, right? Okay. What did I do? I discovered this edge. Then what is unvisited? C is there. Maybe I'll go here, and then I'll say 9, 10. There's nothing to do, right? Okay. Then what else is left? I mean, A, D, all of them are there. Maybe I'll go to D, right? You know, I'll go to D. 11, then I will discover 12 and 13, right? Because it's already discovered, right? 14, right? And then I'll go to A, 15, 16, right? Okay, it looks bizarre that you know, why am I doing this, right? But my claim is, let's look at the, sort the numbers in decreasing order of post-visit order, right? What will I get? I mean, so what is the largest post-visit guy? Next, sorry, yeah, F, C, okay, okay, this will be a topological sort of this DAG, okay, it doesn't matter which way you sort it, okay, all right, okay. You know, any way you discover a DAG, I mean, you explore a DAG, if you sort it according to the decreasing post-visit order, you will get a topological sort. All right? Okay, that's nice. Okay, what is it, right? Okay. Okay, all right. So I want, why am I doing all this? You may say, you know, he's wasting our time, but for a good reason, right? You know, otherwise we can't understand this algorithm. Okay. Okay, remember the problem we were trying to solve. I give you a directed graph, and I want to find all its strong connected components. Yeah? Yeah? I want to find all its strong connected components. Right? Is the problem clear? Yeah? How can we do it? We saw a naive algorithm, right? What is a naive algorithm? The naive algorithm is, look at a node, find its strong connected component. That we can do efficiently. How? How do you find the strong connected component containing a node? You would find what all nodes it can reach, find all the nodes that can reach, and take the intersection. Yeah? Okay, just recapping, yeah? So for a given node, you can find the strong connected component containing it in linear time. But then you have to do it for one more node, right? Okay, so that will take n times n plus m potentially, right? Now the question is, can we do it in one linear time? I mean, in essentially the same time as exploring the graph once. Okay, all right. So I want to give you this graph. I want to produce all these guys in linear time. How can I do it? Right? Okay. I'm not going to be able to prove it. I'm going to show you what Tarjan came up with. Okay. And then actually a simpler algorithm that somebody came up with, right? Okay. So what is the key idea, right? The key idea is this, right? Remember, if I give you this graph, this is what? The meta graph of that, right? So what is this graph? This is a graph where I shrink each strong connected component into one vertex, right? Okay. And what property does this graph have? It's a DAG, right? Yeah? Okay. So here is a thought experiment or a wishful thinking algorithm, right? What is the idea? Okay. Suppose remember every DAG has a sink, right? Yeah? Suppose by magic I told you that, oh look, this vertex, this is a sink of, I tell you one vertex in the sink component of this DAG. Okay, what is one vertex in the sink component of this DAG? In this case, there's only one sink, right? What is the sink in this DAG? This vertex, and there's only one vertex in this happens, right? It's H, okay? But there could be multiple vertices, yeah? Oh, sorry, G, okay? Okay, suppose I start exploring the graph at G. Suppose I do DFS starting at G, what happens? In this graph, if I start DFS at G, what will I discover? I'll discover G, right? Okay, no, but I'm saying that if I knew that G was in the sink component of this DAG, I don't know how, because I'm trying to find that DAG, but if I magically knew that G was in a sink component and I actually started my DFS there, what work do I do? No, I'm not doing the entire DFS. I'm just doing the DFS exploring from that vertex. If I just explore from that vertex, what will I discover? Yeah? Yeah, I will find only the component that is containing it, no? If I just explore the graph just from that vertex, I'll only find the component containing that, right? In this case, it's only one vertex, right? Okay, but I want to remember, if I explore the graph from that vertex, the amount of work I do is only proportional to what I discover. Okay, of course, I have to set up the initial data structures and stuff, but once I start doing the exploration in that portion of the graph, I only discover that component. Okay? Okay, so if I can do that, somehow if I magically knew that this was a vertex in the sink component and I started my exploration there, I will only discover that component. I can remove it, and if I can again magically find somehow the vertex in the next sink component, I only explore from one vertex in that, I discover that. Okay, so what I'm trying to say is that if I knew a topological sort of this DAG somehow, without knowing this DAG, if I knew a topological sort of the DAG, I will be in good shape, no? Yeah, I can find a sink, explore that, remove that, find the next sink, explore that, but the total work I do will be proportional to only the size of the graph. Why? Because when I'm exploring this, I don't do any work other than what this can reach. I mean, this can reach, and then I do work proportional to this, then I do work proportional to this, and then I do work proportional to this. Okay? But this seems all wishful thinking, right? Okay, so this is really indeed wishful thinking, but okay. So the point is, how can I get the topological sort of the DAG I'm trying to discover? I claim DFS gives it to me, okay? All right? I claim DFS gives it to me. So, okay, so instead of explaining to you it's a complicated algorithm. I'm trying to do this only to inspire you, not that this algorithm is the detail, something that you need to remember, right? We won't need to remember the details of this, right? The point I'm trying to make in this lecture is really that DFS has important properties that can be exploited algorithmically, but you need to know a lot about the properties, right? Okay, okay. So here is a simple algorithm that gives you linear time algorithm for this problem. The code is just this, okay? What is the code? You take the graph G, reverse it. Okay? Everybody knows what reversing the graph is, right? Right? We take it. You compute the DFS of the reverse, like we did. Okay? What do you get? You get some information about post orders and pre-orders, right? Some numbers. So you sort it according to decreasing post order numbering of the DFS of the reverse of the graph. I'll tell you why the reverse, right? And now you do a second DFS, but not in arbitrary fashion, but using the order you got from the first DFS. Okay? That means you start exploring the graph in, what is the first vertex you'll explore from the graph? The guy from the ordering you got from the first DFS in the reverse of the graph. Okay? That's it. The algorithm is that. Okay? Is it clear what the algorithm is? I'll tell you what it solves. Okay. Let me run the algorithm and then I'll tell you what it solves. Okay, here is the graph G, and this is the reverse of the graph. Well, you can see that I reversed everything. Okay? Okay? So far so good. I do a DFS on this graph. Okay? I do some arbitrary DFS, right? I started with, in this graph, I started with A in the reverse of this graph. So I get some numbering, no? What is the numbering I got? This is the numbering I got. I sorted according to post-visit order, right? The reverse, right? What is the last guy here? G is the last guy. Some magic happened, no? Okay. Did you see that G is the last guy here? Okay. Now I do a DFS starting with the original graph, but using the numbering, right? I explore the graph from G. What happens? I get G. I remove it. Okay, what's the next guy in the ordering? H. Again magic is happening, right? Okay, so I explore from H. What happens? I remove H. Then what is the next guy? Sorry? B. So I explore from B. What happens? I get B, F, no? And then I do that, and what am I left with? A, and I discover. Yeah. Okay, you see that? Okay? Okay. All right. This magic is not a coincidence. Okay? Yeah. Okay. Then shall we run the algorithm again? Yeah? The algorithm is very simple, right? What is the algorithm? Here is the code for the algorithm. It first does the DFS in the reverse of the graph. Okay? Arbitrarily, it doesn't care. It can break ties arbitrarily, right? But once it finishes the DFS, what do you get? You get a post-visit numbering, right? Okay, now the second DFS you cannot do arbitrarily. Okay, the second DFS you use that ordering and say, who will I start the DFS with? The first guy in that ordering, right? That's the largest post-visit in the right. And whoever I discover in that, I remove it. That's one strong connected component. Okay, and then you find that I'm done with that. Then the next guy left in that ordering, I do a DFS. I continue the DFS, but I'm doing this in this order. So this way, I'll discover all the strong connected components. Yeah, but how do we do DFS, right? Let's so okay. Again, just to show nice pretty figures, right? This is G. This is the reverse. I did an arbitrary DFS according to some choices. I don't care. I get a numbering. The numbering is, I know G, H, whatever, right? G, H, B, F, E, A, C, A, D, C, right? That's the numbering, yeah? Yeah, so yeah? Yeah, any way you want. Yeah. Yes. Yeah. It's effectively the source when we do the reverse of the graph. It's effectively the source, and so that guy will be the last. We need a sink, but post-visit order gives us sources. So we reverse the graph to make sources sinks, and we do this. Okay, the whole point of this is you won't remember any of this, right? Okay, but the thing is, the point is you agree that if it is correct, it is linear time, right? Okay, because we are doing 2 DFSs, right? That's it, right? Okay. The point is that it will give you all the right thing. I'm not going to prove it because it's a pain to prove it and it's not easy, right? But this is why Arjun won the Turing Award, okay? In the sense that, you know, DFS gives you this information that you can exploit algorithmically, right? Okay? All right, the first DFS is giving you information implicitly about the, see, we are doing DFS in this, but it is giving you information implicitly about this DAG. Okay, the numbering is giving information about implicitly about this DAG, which you can exploit in the next time you do DFS. Okay, is it clear? I'm not going to say anything more. Okay, other than the fact that you should know that given a directed graph, you can compute the strong connected components and the DAG representation in linear time. Okay, you need to remember that you can do this in linear time. Okay, not how, right? Not even the algorithm. You have a black box that given a directed graph will compute this graph for you in linear time. All the strong connected components and its representation as a DAG in linear time. Okay, you don't have to remember how you did it. Okay, is that okay? You will need it in your homework and in your exams, right? The fact that you can go from this graph to this graph in linear time. Yeah? Okay? Yeah? That's all I want, yeah. That's because it is implicitly doing, see, imagine what DFS in this graph is doing here, right? Right, you know, I claim that it will explore this graph. I mean, while exploring this graph is essentially exploring this DAG too. And the post-visit numbering gives you, so if you do it, I claim the following. If you do a DFS of this graph, which vertex will have the largest post-visit number? Any DFS of this graph, I claim something nice. What will happen? Which vertex will have the largest post-visit number if I do a DFS of this? No. In the reverse it will be G, but in this graph which will it be? One of the vertices of ACD. Why? Because this is the only source in this DAG, right? Okay. DFS of this graph, see, nobody can reach ACD, no? See, if I start the DFS in ACD, what will happen in this graph? See, if I start the DFS in this graph starting from ACD, I'll discover everything, no? Yeah? And then clearly the starting guy will have the largest post-visit number. Yeah? Okay, suppose I did not start the DFS on ACD. If I start from BEF, what will happen? I won't get to ACD, no? But then eventually I have to visit everybody. So eventually I'll have to visit somebody from here by picking that guy in the next DFS, right? So I claim that if you do a DFS in this graph, irrespective of the order, the guy with the largest post-visit number will be somebody from ACD. Okay? That means we'll find the largest post-visit guy will be from a source. But we wanted sinks, so we reverse the graph. Okay? That's the idea, right? Yeah. You need to. Okay. Yeah, no, you need to. Okay. All right. It's not obvious, but you need to. Okay. Yeah. Yeah, certain property is not true, but if you look at the notes, you'll see that. Okay. Yeah. Nothing. See, that's the beauty of this algorithm is that the first DFS is completely arbitrary, you know. It's still giving you a lot of information implicitly. That even though it looks useless from a top level, you know, what is it doing really, right? You know, it is giving you very good information. Okay. So the point of this is not to make you remember DFS and all its fancy properties of what it is doing, but to show you that you can get better algorithms if you are, you know, pay more attention to the details of what it is doing. Okay. So DFS is interesting not because it's yet another search strategy, but because it explores the graph in a certain nice way. Okay? Okay. All right, that's all I want to say about DFS. You can solve this problem in linear time, finding all the strong connected components. and you need to know that you can do it, and it doesn't matter how you do it, but that's the algorithm. Okay, I hope the pictures are pretty. Right? Sariel spent a lot of time on this. I used to just do it, draw it, but he converted it into this and said, okay, I'm not going to explain the proof. I'll just go show you pictures, right? And see the code, right? It's always, you can implement this in 20 lines, basically, right? And it's really, really beautiful algorithm. So there's a story connected to this particular algorithm, okay? This algorithm where you reverse the graph and do DFS. So the original algorithm of Tarzan uses stacks. He didn't, a very complicated looking algorithm, even though it is 20 lines, it's a very detailed algorithm. Push this in the stack, pop that out of the stack, do this, do that. It was hard to actually make sense of it, right? So this particular algorithm I described was discovered by a professor at Johns Hopkins because he was trying to teach this lecture. He forgot the algorithm of Tarzan. Okay, and so 1 hour before the lecture, he was scratching his head. How do I describe it? How do I prove it? He came up with this algorithm. He knew the proof and the intuition behind the algorithm, and he came up with this particular simple form because he had to teach it, and he forgot the original algorithm. Okay, so it's nice that but that's a nice. Okay, we don't have much time to let's do some application. To how many of you use Makefiles, by the way? Okay, at least Makefiles, right? Okay, and if you had to write make, what do you think drives make? Yeah, okay, good. Okay, okay. So I don't know, with the current trend on using this integrated IDEs, right? You don't use a terminal so much anymore. So I don't know if you even see make, right? Maybe you don't see make. Okay, so I just wanted to, this is how, when I was a student, I used to write this C files. So what does the Makefile specify, right? Makefile is really specifying a dependency graph, no? When you write a Makefile, you're saying what depends on what. Okay, so that's a directed graph. How do you know whether it's a good dependency graph or not? What algorithm do you use? Sorry? Yeah, you have to know whether a Makefile is consistent by checking whether there are cycles or not. Yeah? That's the first algorithmic task that Make does, right? Is your specification meaningful by checking whether it has cycles or not, right? So that's the thing. The algorithm you use is given a directed graph. Is there a cycle in it, right? That's the algorithm. Okay, if it is reasonable, what order should the files be compiled? Yeah, you need to do topological sort of that graph, right? Is that clear? That's the order in which you need to compile, right? Okay, if it is not reasonable, how do you provide the debugging information? What do you want to output? Yeah, you have to output at least one cycle, no? Okay, that's the right. Okay, so this problem is interesting, right? If I change a file, what should I recompile? Yeah, so how do you figure that out? Yeah. The reach of? Yeah, so okay, now you have to think, which way did we draw the dependency graph, right? What does this edge mean? It depends on how you define the graph, right? Because you can reverse the graph too, right? I put an arrow from here to here if this depends on this, but you could flip it too, right? So, but what is this computation then, right? The source is what? No, this graph is directed acyclic graph, no? Yeah. Yeah, suppose I change this, what should I recompile? Yeah, right, I find all the vertices that can be reached by this, right? and I should recompile all of them. Yeah? That clear? Yeah? Okay? So that's another reachability computation, right? You don't need to use DFS. You can just do reachability, right? Agreed? Okay. So that's, I mean, I just wanted to illustrate that even in simple routines you need these graph algorithms, and when you have large graphs, okay, so I don't have much time, so I just want you to read something for me before we come back from the break. So the next lecture will be on shortest paths and Dijkstra's algorithm, which you've seen before maybe, but not maybe the proof, right? Everybody has seen breadth first search at some level, no? Yeah? Okay. How do you want to think about breadth first search? What does breadth first search do for you? Why is breadth first search interesting? Yeah, but what does it give you? Sorry? Yeah, so breadth first search is really a shortest path algorithm, right? It is a shortest path algorithm when the edges have only length 1. Yeah? Okay. All right. So that's not the only reason breadth first search is interesting. I mean, of course, that's the main reason why it's interesting. So breadth first search is interesting because it allows you to explore the graph in increasing order of distances. Yeah? As opposed to DFS, which is good at exploring the graph structure. Differences, right? And typically people say breadth first search is queue, depth first search is stack. Right? Of course, it's an implementation wise, that is how it is, right? You can get depth first search by changing the data structure to a stack and breadth first search. And that's a completely useless way of thinking about the algorithms. As an algorithm designer, you shouldn't think about the implementation first. You say, what is it doing for me, right? I mean, implementation is important, right? But that's to make it fast, right? Or to make it crisp. But as an algorithm designer, I should say, does breadth first search do something interesting for me, right? If it doesn't do anything interesting, then it's not valuable, right? So it does because it explores the, okay. Not only that, you have to ask, does it give me some information about the graph structure, and can I exploit it algorithmically for other purposes? Not just because it will give me distances, okay? And it turns out it does, right? And but you know, I won't do the Q version of it because you have seen it all many times. But that's not actually very useful, okay? You want to think about depth first search in a little bit different way, okay? You want to think about depth first search really like this, okay? That before you do breadth first search, let's imagine I look at a graph and a vertex and say, let's order the vertices in increasing order of distance from that vertex, okay? So S is at distance 0 from itself. Let's look at all the vertices at distance 1 from it, all vertices at distance 2, all vertices at distance 3, and so on, right? So level I is all the vertices at distance I from S, right? Now instead of saying breadth first search will discover those levels for me, let's flip it around and actually discover those levels by an algorithm rather than using a specific algorithm, okay? And it follows inductively, right? You know, what are vertices at level I? These are vertices at precisely the distance I from the vertex, start vertex S, okay? So S is at level 0 because it is distance 0 from itself. Given that we know vertices of distance 1 to 0 to I, can I discover vertices at distance I plus 1? What are those, right? The vertices at distance I plus 1 are precisely the neighbors of vertices at level I, which have not already been discovered, right? So it's better to design breadth first search not as a queue data structure, but simply as saying, you know, I'm going to discover vertices in increasing order of distance from S. Explicitly, not implicitly, okay? So that will help us understand shortest path algorithms and other properties, right? So this is how I prefer to think of breadth first search in this fashion. You start with the vertex S, It is at level 0 because it's at distance 0 from each other. While the level Li is not empty, you explore all the vertices at level Li and find all the vertices that you have discovered that have not already been visited. They will be in level Li plus 1. Okay? So it naturally gives you these levels, right? Li plus 1, Li plus 2, and so on, right? Starting from Earth, and that will give you a tree too if you do it in a proper way. And it is easy to prove because of the way we designed the algorithm that we are going to discover vertices in increasing order of distance from S. It's very hard actually to prove that BFS gives you the vertices in increasing order of distances. If you actually formally try to prove that using a Q data structure you will get in increasing order of distances, it's very painful. Try proving it. Okay? It's actually like, oh, what is the Q doing? While if you actually change the algorithm, it's very easy. Okay? So, so this also runs in a linear time. And what is important though is that these levels have some very nice property. So, okay, if I start with 1, what is level 0? This is level 0. What is at level 1? 2, 3. What is level 3? Sorry, level 2, right? And this is at, sorry, level 2, and this is at level 3, okay? Okay, so S is at level 0, level 1, this is an undirected graph, and we'll see that level 2, right? You know, you have edges going. What is one nice property about BFS exploration? Not levels, but in an undirected graph, a very nice property holds true. Let's look at any edge which is not in the graph, in the tree. Where are edges of the graph? Yeah? Yeah, right. In an undirected graph, I cannot have an edge from level 1 to anything other than the previous level or the next level. Yeah? I cannot have a level 1 to level 3, right? Okay. Can I have the edges within the level? Yes, you can have edges within the level, right? So but the only edges in the undirected graph are between edges and levels or within a level. It's a very important property, okay, of breadth. What about directed graphs, by the way? Okay, if I do directed graphs, what property is true? Sorry? No, start at a source. What property is true about the levels again? The similar to what we had in undirected graph. You cannot have an edge from a level forward to a level which is not right next to it. So I cannot have an edge from level L1 to L3, no? Because if there was an edge from level L1 to L3, then this guy should be at level 2. Yeah, no, but the thing is, I can have an edge from level 3 to level 1 going back. Okay? See, in a directed graph, I cannot have an edge from a level Li going down to level Li plus 2 or bigger. But it doesn't prevent me from having an edge from Li plus 2 to Li. Okay? Okay, that's the distinction between undirected graphs and directed graphs. I can have backward edges going up any number of levels. I can have an edge going all the way from here back to L0, right? That's not disallowed, and it will happen. So this is a big difference between undirected graphs and directed graphs in BFS. Okay, that's another property to keep in mind. Okay, BFS is very easy, but don't think of it as a Q data structure. Think of it as exploring vertices in increasing order of distance, and what properties does it give you? Okay, all right. We'll have a good break, relax, and we'll see you in.